Well, hello, welcome again to Math 315. This is the third recording in Chapter 4, and we're looking at continuity, limits of functions and continuity of functions. Before we continue on to look at continuity, I thought I might just put up a couple of little pictures to show you why it's important to have these more formal definitions rather than simply plugging numbers into formulae. So, for example, if I look at this function, I got the computer to plot this one. This is the graph of the function sine of 1 over x. And now, if you ask the question, what is happening as you go towards 0, if you try and take a limit of this as x goes towards 0, in other words, can you make this function continuous at x is 0? And it's not clear at all from the picture. The computer just goes crazy. The curve is zipping up and down, and it's not clear at all what on earth's happening in here. So simply drawing pictures of functions is not going to be sufficient to properly define what is going on. On the other hand, and in fact we will prove in fact that this limit in fact doesn't exist. It actually doesn't make any sense as you go towards 0. This doesn't approach any finite number. On the other hand, I got the computer also to draw the function x times sine 1 on x if x is not 0. And again, you ask the limit. Now, we have looked at this limit before, I think, and we've shown that this limit does in fact exist and go to 0. Again, if you draw the picture, it's not immediately clear exactly what's happening around here. It seems to be going a bit crazy as you get closer and closer to 0, but is there a finite limit here? Can't just tell that by looking at the picture. And another example of a function that we will come back and look at a little bit later is this one. This one's defined in terms of an infinite series. In fact, it turns out it's this infinite series here. It's the sum. We'll look at this one a bit later, but it's the sum n equals 1 to infinity 1 and 2 to the n cos of 4 to the n times x. And if you try and get, now of course I can't draw this using a computer because it can't cope with infinity here. So what I did was I made this, I think, 200, and I got it just to try and draw some kind of approximation to it. And look at this crazy function that we get. It's not clear at all what's even happening as we get towards 0. What's happening to the function? Well, in fact, it's probably because the way I did the scale, this actually, all this stuff continues but much higher up because of the scaling question. But what's actually happening here, it's doing crazy things. And so to deal with functions in general, this is one of the reasons why we need to go to these more formal definitions of things so that we can properly analyze everything. So I thought I'd just mention those ones here. And we move on now to look at continuity at a point. And we're going to suppose we've got a function f is defined at and near some point A. And we're going to say that f is continuous at A if, as you take a limit of the function as x gets closer to A, then that a limit exists and is equal to the value of the function at A. So note that there are two issues here. This limit here has to exist in the first place, and it's got to equal f of A, the value of the function at A. And if that happens, that's going to be our definition, our basic definition of f being continuous. Now, of course, we can interpret this limit, as we will in a moment, using epsilons and deltas, but this is going to be the way we're going to check for continuity. So just as a simple example, we're going to show that use the definition above to explain why this thing here is continuous at 1. This function here is continuous at 1. And this is a very simple example, and all you have to do with in a situation like this, here it is. So there's the function at x equals 1. I'm going to evaluate what happens at x equals 1. So you plug in 1, you get 5. And then I'm simply going to say, well, what's the limit as x goes to 1? Well, that's easy. Again, you just plug in 1, you get 5. And of course, that's equal to f of 1. So as I approach 1, the function's getting closer and closer to 5, and 5 is the function value, and so f is continuous. And that's all we have to do there. That's pretty easy. There's a slightly more intricate example, but not very much more difficult, is this one. It's a split definition function. Here we've got the function x cubed minus 8 on x minus 2. That's if x is not equal to 2. And I'm going to give it the value 12 when x equals 2. Notice you can't put 2 into the top formula because you get 0 over 0. And I claim that if I make the value 12 at x equals 2, then it makes the function continuous. So I'm going to prove the function is continuous at x equals 2. So here is the solution to that. So there's our function. F of 2 is 12. We were given that in the definition of the function. And all I'm going to do is I'm going to take a limit now of as x goes to 2 of f of x. So I want the limit as x goes to 2 of x cubed minus 8 on x minus 2. Now you can't put 2 in here, of course, because you get 0 over 0. So we do our usual trick. We're going to factorise the top. It's a difference of 2 cubes. So this is x cubed minus 2 cubed. So you write them down uncubed. It's x minus 2. And the rule I learnt when I was young was to square the first, square the second, times them together and change the sign, and that was our difference of 2 cubes. We can then cancel out these two terms. X is not 2 at the moment. We're getting close to 2, but x is not 2, so I can cancel these terms out, and I just get x squared plus 2x plus 4. Now I can substitute in x as 2 in, because nothing wrong with that. I get 2 squared is 4 plus 4 plus 4, which gives me 12. And that was, in fact, the value of the function at 2. So we've shown that the limit as x goes to 2 of f of x exists and equals 12. And that is the value of the function at x is 2. So our conclusion then is that f is continuous at x equals 2. And that's all we had to do there with that one. So that's, I hope, a fairly straightforward way of defining what we mean by continuity at a point. Now this is continuity at a particular point at this stage. We'll talk about continuity more generally in a moment, but that's the basic key idea there. I'll do one more, a couple more examples here. Here's another example here. We're going to show that this function, this is x over the absolute value of x. If x is not 0, you can't put 0 in, you get 0 over 0 again. And I'm going to put the function value equal to a if x takes the value 0. And we're going to show here that this function, doesn't matter what value of a I pick, this function is not continuous for any value of a. It's not continuous for any value of a. I can't put a number in here and make this function continuous. You might think about the graph of this. I'll do this, put this over the side here. You might think about the graph of this function. Remembering again the definition of absolute value of x. So the absolute value of x is equal to x if x is positive, and it equals minus x if x is negative. So that's our definition of absolute value. So if x is positive, then this is just x over x. And x is not 0, so I'll put a little hole here. So if x is positive, if my x is over here, this is just x over x, which is 1. Now if x is negative, then by definition, absolute value of x is minus x. So that means this takes the value minus 1. If x is negative. And you can sort of see from the picture that there's no way I can make these join up. You can't put an a value here that's going to make it continuous. So you can see what's happening graphically here. But now we want to go back and show this using the definition of our limit. So here is the solution to this one. So what we do is we need to look at the limit. We need to see what's happening as x goes to 0. We need to look at this limit. We're going to show, of course, this limit doesn't exist. So, because this thing changes, we saw from that little picture, it changes depending on whether x is positive or negative. I'm going to take a right-hand limit firstly. I'm going to go towards x from above. I'm going to take a right-hand limit. This is typically what you do when you've got functions involving absolute values and things. You typically have to look at left and right limits. So I'm going to have a look at what happens when I go to 0 from the positive side. And so I just copy that down. There's my function. Now if x is positive, as I mentioned before, the absolute value of x is just x. And x over x is 1. And now x can do what it likes. 1 is still 1, so the limit is going to be 1 from that side. Now we're then going to look at what happens from the other side. We're going to look at it from the left-hand side. This is the left limit, so we're approaching 0 from below. That is, we're thinking of x being a negative number, firstly. So that's the limit. I plug in the function. The limit as x goes to 0 from below of x on absolute value of x. Now if x is negative, as I mentioned before, absolute value of x is minus x if x is negative. So these cancel out, then I get minus 1, and then the limit is just minus 1. So these are not equal. And so that means the limit as x goes to 0 does not exist. You go in one direction, you get 1. You go in the opposite direction, you get minus 1. These aren't the same, so the limit does not exist. And that means, hence, f is not continuous for any value of a, because the limit doesn't exist. I want to do just one more example here. We're now going to consider this function. Again, a split definition function. We're gluing together two functions. This idea of gluing functions together, this split definition, actually is very, very important in the applications of calculus. There are things called splines, which are used constantly in computer graphics and so on, where you're gluing together pieces of functions. And so things like continuity and so on are important ideas there. So I'm going to try and glue together e to the ax plus b, that's if x is bigger or equal to 0. And I'm going to try and glue that together with a cos curve if x is less than 0. Now I want this function to be continuous, so I want to know what values of a and b, what kind of numbers can I put in for a and b that will make this function continuous at x is 0. I want to be able to glue the functions together so that when I finish off, I've got the cos curve if x is less than 0, and then I want it to join nicely onto e to the ax plus b. So again, I'll go through the solution of this one. And again, because it's a split definition, we're going to be using left and right limits again. So the limit as x goes to 0 from above, so I'm going to be taking this one, this is x positive of f of x, is the limit as x goes to 0 from above. I've got to use the first part, the e to the ax plus b, because that's the formula you use if x is positive, and I'm thinking of x being to the right of 0, so it's a right-hand limit, so x is positive. Now I can just plug in 0 into this, so that just gives me e to the b. I put x as 0, I get e to the b. I can't do much more with that at the minute. So that's what's happening on this curve. As I get close to 0, then I'm getting close and close to e to the b, and in fact at x is 0, which is in the definition, I just get e to the b. If I take the left-hand limit, so I'm now taking the limit as x goes to 0 from below, now that means I'm using this part of the definition, because this is for x, this is what it looks like if x is negative, and here I'm going from towards 0 but from the other side, from the negative side. Cos of 0, of course, is just 1. So if we want f to be continuous at x is 0, then these two have to be equal to each other. So e to the b has to be 1. Well, that's easy now. What number? E to the what gives me 1? Well, e to the 0 gives me 1. So b, in order for these two functions to glue together, at least to be continuous, we need b to be 0. Notice it didn't give us any information at all about a. So at this stage, just to be continuous, a can be any real number. A can be any real number. So we can say that f is continuous at x equals 0. By the way, I'm going to use this CTS quite commonly. CTS is just an abbreviation for continuous, which I've used above in fact as well. So CTS means continuous. It's continuous at x equals 0 if b is 0 and a can be anything. So a belongs to the set of real numbers. A can be any real number you like. Now, because we define things in terms of limits, continuity in terms of limits, we can also rewrite our definition of continuity using epsilons and deltas. So we can use our limit definition to write this using epsilons and deltas, and here it is. So what we're saying is that the limit as x goes to a of f of x is equal to f of a, and that's the same as saying given epsilon bigger than naught. So I tell you the epsilon width, you can find a delta such that x minus a less than delta implies f of x minus f of a is less than epsilon. It's exactly the same definition we had for limits, except I'm just replacing the L now with f of a. So I'll go through an example, and here of course again is the picture. It's the same picture we had before. Last time we had an L here, now we've got an A. So it simply says that I've got f of a, I go up and down a little bit, then there's got to be around the point A here, there's got to be a little delta interval. So this is a minus delta, a plus delta. So that if I take any x inside that interval, then f of x is inside the same band here. It's the same picture we had before and the same idea. So I'll just go through an example of that. You'll see again it's very similar to what we had before. We're going to again prove using the above definition that this is continuous at x is 1. Now in tests and things I will be very explicit. If I want an epsilon delta proof, then I will explicitly say epsilon delta. Otherwise you just do it the way we did it in the previous example. So here's our epsilon delta proof. So given epsilon delta proof that f of x is 3x plus 2 is continuous at x is 1. So we do the usual thing for all epsilon bigger than naught, put delta equal to, I don't know yet, we leave a gap. Then if x minus 1 is less than delta, because we're looking at the point 1, then we want f of x minus f of 1. So f of x is 3x plus 2, f of 1 is 5, so 3x plus 2 minus 5 is 3x minus 3. We can take the 3 out of the absolute value sign, so I get 3x minus 1. And finally then I can say, look, that's less than delta, so this is less than 3 delta. And how big did I want it? Well, I wanted it less than epsilon, so I'm just going to put this equal to epsilon, and then I go back and fill in the gap here, so I solve this for delta, this is epsilon over 3. So it's very similar to the examples we've done before, except instead of L we now have f of a. Slightly more difficult example. We're going to prove that sine of x is continuous at x equals a. Now this is somewhat more to do, as you'll see. It's actually not quite so bad, and I give you a little help here. I give you this difference of two sines formula, which you may have come across before. You don't have to memorize this formula. I don't remember it. I rederive it if I need it every time. There's things like this in the high school syllabus, I think in the extension courses, these differences. When I was at school we had to learn these off by heart, but I must confess I never did. I just learned how to derive them every time. So I give you that particular identity here. We're going to use that to prove sine is continuous everywhere. At any point A, we're going to prove sine is continuous. something that you've taken for granted all the way through high school, that when you draw the sine curve, it's a nice smooth curve. You can draw it without taking your pen off. We're now going to actually, for the first time, prove that formally using our epsilons and deltas. And you'll see the proof's not quite so bad as you might imagine, given that little formula there. So here it is, I'm going to prove that. So we give the usual mantra, give an epsilon bigger than naught, put delta equal to I don't know yet. Then if x and a are within delta of each other, that is if the absolute value of x minus a is less than delta, then I need to look at the difference between sine of x and sine of a. Now that's where I'm going to use that formula that I mentioned there. Let me just put it here again so you can see how I'm using it here. Let's move this up a bit here. So here I've got sine of x minus sine of a, so I'm just putting y is a in. So I get 2 cos x plus a on 2 sine x minus a on 2. So I'm just plugging that straight into the formula that we were given. Now I have to use here a couple of basic facts. Firstly, that the absolute value of sine of t is less or equal to t. Now that's probably a result I think we have mentioned before. Graphically, all it's saying is that if you look at, just take t positive for the moment, if you look at the sine of t, and if you draw the line y equals t, then all of the sine values are less than the values along this line y equals t. So that's a well-known fact perhaps, but perhaps not one that you instantly recognise. But the absolute value of sine of t is less than or equal to t. On the other hand, you do know the absolute value of cos, it can't be any bigger than 1. So that means this difference here, sine of x minus sine of a, is less or equal to, I've got a 2 here, this can't be any bigger than 1, and then sine of t is less than the absolute value of t, so sine of x minus a on 2 is less or equal to x minus a on 2. These now cancel out, and I just get absolute value x minus a. And we were given up here that that was less than delta. I wanted the difference less than epsilon, so I put this equal to epsilon. And now I go back and fill in the gap. I just have delta equal to epsilon, and I've satisfied the definition. So if I take a point A that's within delta of x, then sine of a, or sine of x minus sine of a, tracing that through, is less than the width of the band, epsilon. And that means the sine is continuous. Now that's a somewhat harder example, and if I didn't give you this formula here of how to do the difference of sines, and then I had to give you this as well to put it all together. We'll have a look at another example here where we're going to use left and right limits to prove that this function is not continuous at x equals a. And I'm not going to do this with the epsilon delta. I'm just going to use, it just says use left and right limits to prove that this function is not continuous. So that's what I'm going to do. So here it is. Here's our example. So we've got f of x is x squared if x is less than 1, and it's 2 if x is bigger than 1. Now we have to do this using limits, but you can see what's happening graphically. If I draw a little picture of this, this is just x squared if x is less than 1. So there's x squared if x is less than 1. And of course, as you get closer to 1, there's a hole here. And it's equal to 2 if x is bigger than 1, but of course this is 1 here, 2 is actually up here. So you can see graphically the function's not continuous, but we need to show this using our left and right limits. So I take the limit as x goes to 1 from above, that is, I'm looking at x going from 1 from this side, and the function value, if x is bigger than 1, is just 2. So the limit this way is 2. That is, as I move this in this direction, I'm getting closer and closer to 2. On the other hand, if you take the limit as x goes to 1 from below, then from this side I'm using x squared, and the limit as x goes to 1 of x squared is just 1, and that doesn't equal f of 1, which is 2, because f of 1 takes the value 2. So these are not equal to each other, so that means the limit, so I should say that means the limit then as x goes to 1 of f of x does not exist. Does not exist. And that says f is not continuous, CTS, at x equals 1. Okay, so in practice these are not that difficult to write out. Slightly harder example just to finish off this section with, and then we'll come back and look at this theorem a bit later. We're just going to finish off with this example here. So using the negation of the definition, we can say that f is not continuous at x is a if there is an epsilon. So I build an epsilon band. So again, we're going to think of a picture like this. So here's my function. Here's a function which is not continuous at x equals a. So what it says is, I can find an epsilon bigger than 0. So I'm going to put a little epsilon band around here. So that for any delta I construct, for any delta, no matter how close I try and go to here, there is an x inside this interval, and I'm going to take my x to be there, so that if I now take f of x, so there's my f of x up here, and look, that one's not inside the epsilon band. So this is my f of a. This is f of a plus epsilon. This is f of a minus epsilon. So no matter, I can find an epsilon here. I can draw a little band here, so that no matter how small I make my delta, so this is a minus delta, a plus delta, no matter how small I make this, I can always find an x inside here, so that f of x is outside the band. And that's a way of describing, or a way of capturing, a function which is not continuous. Now, I'm not going to expect you to do too much on this particular thing, but I wanted to show you this rather fascinating example. Here I've got a function f of x which is minus 1 if x is rational, and 1 if x is irrational. Now you might just think about what kind of graph, what the graph of this might look like. So the picture of this is going to look something like this. And it's impossible to draw it perfectly, but so here's 1 and here's minus 1. Now 0 is rational, so in fact it's going to go through that point. It's going to go through this point. And for example, 1 is rational, so at 1 it's going to be there. A half is rational. You're going to get a whole lot of little dots here. But then you might, for example, have 1 on root 2 in here, and that's going to be irrational, so that takes the value 1. So you can get a whole lot of, there'll be a hole at that point. You get a whole lot of dots in here. So the graph of the function, it looks very strange. This is 1 here. It looks very strange. It's a perfectly good function. But it looks like this. So whenever there's a dot here, there isn't one here. Whenever there's a dot here, there isn't one here. And that's our function. Now, it doesn't look very continuous, and in fact, it's not continuous anywhere. You can't possibly draw this without taking a pen out. It's not continuous everywhere. And I'll just give a little proof of that using our definition up here. So if you take x naught to be a rational number, so I take any x naught rational, and I take epsilon to be a half. So I take an x naught here, which is rational. Now if it's rational, its function value is there. And I'm going to put epsilon to be a half. So I'm going to draw a little epsilon band around here, around this -1. Now, we can always find an x that's irrational, that's as close as we like to my x naught. So I draw my little epsilon band around here. So there's the epsilon band there, and there's the bit below. And I can always take an x that's near this one. For any delta, I can always find an irrational number that's as close as I like to my x naught. But if you work out f of x is up here because x is irrational. And of course, this is not inside the band. So this value up here, this height, this value of 1 is not inside the epsilon band, because I made this a half, so that'll be minus a half minus 1.5, and then if I'm up here, I'm not inside the band. So the difference between these two is 2, and that's bigger than epsilon. Okay, so that's just an interesting example. I don't expect you to be able to reproduce this one, but it's an interesting example of a function which is not continuous anywhere. It's a perfectly good function, sometimes called the ruler function, R-E-L-E-R, and it's not continuous anywhere. So next we'll have a look at a nice theorem that helps us in dealing with functions like sine of 1 over x, and showing that that doesn't have a limit at x is 0.